Alright, so for example 5 it says a soda company wants to design a can of soda that will use the minimal amount of metal. The can must have a volume of 25 cubic inches, and what are going to be the optimal dimensions here? So we're working with a can of soda, so we're working with the outside of the can is going to be called our surface area, and then the volume is what could go in the can, which has to be 25 cubic inches. Okay, so and we want to minimize the amount of metal. So we want to minimize the surface area. So we're going to have to find the minimum of the surface area. And the surface area formula is given here. I'm going to go ahead and write it down here. So see how it's 2 pi r squared plus 2 pi r h. In order for us to be able to find the minimum of this, we're going to have all the same variable here. So we're going to have to use that volume. And if you see, the volume formula here is pi r squared h. And we know the volume is 25. Now, you could really solve for either one. I'm going to solve for h because it's going to be easier to solve for than having to take the square root. So if I solve for h is going to be 25 divided by pi r squared. Okay, so the volume was just given so that you could get one of your variables and solve for it. So now I'm going to go down here to my surface area formula. I'm going to plug in. So 2 pi r squared plus 2 pi r, and now instead of h, we know that is 25 over pi r squared. Now you don't have to simplify, but you can. I'm going to simplify just to make it look a little bit easier here. It's easier to type in the calculator. So we're going to have 2 pi r squared plus, since I have r squared and that r will cancel, and then the pi's will cancel. So that 2 times 25 would just give me 50 over r. So this is our surface area formula with only one variable here instead of having two. So we want to graph this, and we want to find the minimum here. So in your calculator, go to our y equals and clear it out. Alright, we got 2 pi, 2 pi, and you got to use x for r, but x squared plus, I'm going to make a fraction, 50 over r, but I'm going to use 50 over x. I'm going to go ahead and graph and see what happens. So I can kind of see it, but, oh, remember we have 50,000 here. Let's go back to this 50,000. Let's make it 100 and see if that helps. Alright, and I'm going to change my x max not to be so big either. There we go. That's a whole lot better. So let's write down what we did for our window. So for our window, for our x max, we said 50. And for our y max, we just said 100. Okay, so we go to our graph. Sketch our graph here. So what's going on is you actually have a line here, and then this part is where you actually have your minimum. So I want to find this minimum. So we're going to do second trace minimum, number 3. Find your cursor first. There it is. So left side, enter. Right side, enter. Guess, enter again. So you're going to get 1.585. And then beside of that it says 47.331. So this 1.585 is your x, which in this case is your r because that's the letter we were using, and then this 47 is our minimum here. Okay, the question said, what are the optimal dimensions? So because they want us to find dimensions, we're trying to find r and h. So we know that our r is 1.585, and that's going to be inches. To get our height, you're going to plug into this red equation over here, this 25 over pi times 1.585 squared. You can plug that in on the calculator. It should give us 3.168. So that gives us our radius and our height of our can of soda, so that we would use the minimal amount of metal. Okay, and then our last problem, we've actually seen a problem similar to this before. So it says a box company creates a box with no top by cutting squares out of corners of an 18-inch by 22-inch rectangular piece of cardboard. What dimensions will give the box the largest volume? So we are going to have a cardboard box. It says it's 18 by 22. And we're going to cut out squares. So we're going to call these squares X. And then they're going to fold it up. Okay. What dimensions will give it the largest volume? So largest volume means we want to maximize volume. So we have to find an equation for volume and find what the maximum is. So volume equals length times width times height. We're doing a box. So my length here was 22. But you see I'm taking out X and I'm taking out X. So my length is actually going to be 22 minus 2X. My width is 18, but I'm taking out X here and I'm taking out X here. So that's going to be 18 minus 2X. And then your height is what you're cutting out here, these X's. Okay, so I'm going to graph this so we can find the maximum. You do not have to multiply it out. Go ahead and graph. Okay, so I'm going to change my window a little bit. I'll leave the 50. I'm going to change my Y max to 1,000. Alright, that's good. So X max I did 50, Y max 1,000. Okay, and we'll sketch a little graph here. So you see this graph actually has a maximum and a minimum. But we're just trying to maximize. So we just want to find the max. Okay, so to do the max, we're going to do second trace number 4 for max. We're going to do left bound. So move on the left of your max. Hit enter, right bound, hit enter, and then guess and hit enter. So you get 3.284 and then 579.359. So the 3.284 is your X here, and then the 579 is our max. We wanted to figure out what are the dimensions of the box. So the height of the box, your X there is your height of the box. So your height is 3.284, and that's inches. Okay, so remember for your length, we said that was going to be the formula 22 minus 2 times X. So we're going to plug in X. And I'll give us 15.432. That's also inches. And then your width was 18 minus 2x. So we do 18 minus 2 times 3.284. This should give us 11.432. So those are our dimensions that our box will be, and will not have a top on it, to maximize the volume. So we found the maximum there.